hypothesis test for a mean or on a mean for mu. We're testing a mean mu, a population mean. That's a parameter, a population parameter, mu, not a statistic. The null and alternative hypotheses are in terms of mu. Okay, here we go with one of my famous never evers. You should never, ever, 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 never, 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 never see X bars here. No, that's about one of the worst mistakes you can make. You completely misunderstand what hypothesis testing is if you put X bars there. I emphasize that to my business stats students. They still do it sometimes. Please, you guys, don't do it. Okay, I feel like failing somebody for the course if they put X bars there. I don't, but I have that feeling in my heart like, oh, they're completely misunderstanding hypothesis testing, or at least failing on hypothesis testing. Okay, it's always population parameters that go here in these situations, never ever statistics. There are some situations where the null and alternative hypotheses are not really stated so much in terms of parameters, but descriptions. In fact, the chapter 8's got one example of such a null hypothesis where you've got the statement is the data come from a normal distribution, and the alternative is the data do not come from a normal distribution. That would be an example of hypotheses tests that are stated in words. But you still are talking about a population there. The normal distribution is describing a population. It's always about population, never about a sample. So just like before, you'd want to decide what is your research hypothesis. Maybe it's that mu is greater than something. Maybe that it's less than something. Let's do less than something just for the sake of change. I'm just going to make up a number here, 20 or something. If that is the alternative hypothesis, if you, for some reason, think that in a certain situation, a certain population mean is less than 20, then the alternative hypothesis would be the opposite. Excuse me, the null hypothesis would be the opposite of that. Mu would be greater than or equal to 20. But just like before, we usually make it simple and just write in equals. Just keep it in the back of your mind. If mu being less than something is your alternative, in reality, the null would be that mu is greater than or equal to that same something. By the way, I haven't emphasized this. Whatever number is here, that's called the null value. The boundary of the null region, you might say, is the null value, and it's got a symbol mu sub 0 for null value. The fact that this is a less than sign means this is a left-tailed test. And to find, if we want to find the p-value, for example, it'll be the area under a curve to the left of something. Left-tailed test. Okay, so once again, there's a couple different ways you can think about this. You can think about this with critical region and figuring out alpha, the probability of type 1 error, and then based on the critical region and based on an observed value for some test statistic, decide whether you're in the critical region or not. If you are in the critical region, also called the rejection region, you would reject the null. And if you're not, you would fail to reject the null. Or you could compute a p-value, the probability of observing a test statistic as extreme or more extreme than what you actually observe if you assume the null is true. Let's once again do it both ways. However, once there's a complication here. Do we know the population variance or not? Just like with confidence intervals, do we know sigma squared or not? Or alternatively, do we know the population standard deviation or not? Let's do it both ways. First, assuming we know the variance, population variance. Secondly, assuming we don't. Just like with confidence intervals, in the first approach, we'll use Z, and in the second approach, we'll use T. And we'll have to deal with degrees of freedom. So if we know, assume sigma squared is known, Yes, that's unrealistic, but just for the sake of keeping things simple, is just trying to get the idea of it. Say, let's pick easy numbers here. Say sigma squared is 25. So sigma is 5. What should our rejection region be? It's also going to depend on the sample size. Assume n is, what should I pick? Maybe 16. Let's pick something bigger. How about 100 for n? What's the rejection region? Again, also called a critical region. I'll just label it one way here. Oh, you can call it C again. There's a couple different ways this could be thought of. You can either think about the critical or rejection region in terms of values of the sample mean X bar, or probably more common is to think about it in terms of the corresponding Z value. Let's do it the more common way. The corresponding Z value, the set of all Z's such that Z is less than something. Less than what? It's up to you. But what you pick is going to affect what alpha is. Oh, let's just pick maybe negative 1.5. Just to pick something. What am I after? I'm sort of thinking about standardized values, Z values, and wondering what's an extreme Z value. I mean, by the 68, 95, 99.7 rule, with a normal distribution, the area to the left of -3 would be half of 1/2 of 1%. 0.0025. The area to the left of -2, there's 2.5% of the areas to the left of -2 would be 0.025. Right? That's 68, 95, 99.7 rule, about 95% of the probabilities between -2 and +2. So there's 5% of the area to the left of -2 and to the right of +2. By symmetry, half of that, 2.5%, slightly less, would be to the left of -2. If I pick this for the sort of boundary Z value, evidently the area I'm after is going to be a little bit bigger than 2.5%, probably. I don't know, 5% maybe? Maybe somewhere close to 5%. Actually, I'm going to put a less than or equal to here, though it's not a big deal. So that's my rejection region. I could ask, what is the probability of a type 1 error? Alpha, the probability of type 1 error, based on that rejection region, would be the probability that I'm in the rejection region, that Z is less than or equal to, let me make it a capital Z. Capital Z is less than or equal to -1.5, assuming mu is 20. But how do I do that? Well, okay, the assumption that mu is 20 is kind of already going into the calculation. I don't really need to write it there. Okay, I won't write it there. Yes, I am assuming this. Assuming mu is 20 when Z is actually calculated. We will do an example here. We will actually calculate Z. But for the moment, let's just sort of put it in parentheses outside the probability. What is this probability? Use a normal CDF. Normal CDF. Upper being -1.5. About 0.067, close to 6% again. About 0.067. Actually, let's round that to 0.07. So if I use this critical region, this is my rejection or critical region, that'll be my probability of a type 1 error. But how do you actually compute Z in a given situation? You have to have a value of X bar. let me write it as a capital X bar initially, but then we'll ultimately plug in a number and we'll write it as a little X bar. We know that if we are sampling from a normal distribution by the cornerstone theorem, that X bar will be normal as well. And if we're assuming that the mean of the population is truly 20, I could standardize this by subtracting that mean of 20 and dividing by the standard deviation of the sampling distribution of X bar. In general, it's subtracting the null value, which we're assuming is true, and dividing by sigma over square root of n. We know this is going to have a standard normal distribution if I'm sampling from a normal distribution with mean mu0, standard deviation sigma, and sample size n. That was really the cornerstone theorem. What if I'm not sampling from a normal distribution? By the central limit theorem, X bar will be approximately normal with that mean and that standard deviation. And so this will be still a good approximation. How big is big for the central limit theorem? It depends on how skewed from normality your population is. But generally speaking, people might still use this when n is at least 30, is the advice the book gives. You could call this z because it's standard normal. So now let's compute an observed value. Assume we've got a value of little x bar. What is it? Let me just make something up. 18.37. 18.37 is less than 20. Are we going to reject the null? Without actually doing a calculation to convert this to z, you don't know. It's smaller than the null, but is it a statistically significant difference? Is it significantly smaller? What is the corresponding z value? Is it in the rejection region or not? Is it less than negative 1.5 or not? The test stat that we ultimately use is z, is this observed value of little x bar minus the null value over sigma over square root of n. So that's going to be 18.37 minus 20 over sigma was 5, n was 100. This is negative 1.63. Square root of 100 is 10. 5 over 10 is 1/2. We're getting a z value that is significantly far from 0. Negative 1.63 divided by 0.5, negative 3.26 is the observed value of the test statistic in this situation. In terms of z, it's in the critical region. We definitely reject the null here. What's the p-value of the test? I can compute the p-value without thinking about the rejection region. Just like before, the p-value is, like I said before, the probability of observing a test statistic as extreme or more extreme as what you actually observe when the null is true. What's the probability that capital X bar will be less than or equal to 18.37? Notice the less than or equal to. Assuming mu is 20. It's less than or equal to because this is a left-tailed test. Convert to z. You do the exact same calculation you did here, and we get a negative 3.26 here. And you don't have to bother writing it as a conditional probability anymore, because I've already used the assumption that mu is 20. Right up there. What is this probability? It's very small. Normal CDF, negative 3.26. Very small probability here. About 0.00056. Right? 5.5. Oops. Yeah, 5.6 approximately times 10 to the negative 4. You'd bring the decimal to the left 4 spots. Yeah, a very small p-value, certainly smaller than alpha, which was 0.07. So if I want to compare it to alpha, I would certainly say, yes, reject the null. But even if I didn't think about alpha, just looked at the p-value, I'd say that's so small, it would be crazy not to reject the null. I'm going to reject it. You don't have to think about the critical region. But wait a minute. This was all done under the unrealistic assumption that we knew sigma. That's not usually the case. You might argue it's never the case, except maybe in simulations. Well, even in simulations, you might wonder whether your simulation's accurate or not. So what about going back and doing the same exact test? But now let's assume sigma squared is unknown. But just for the sake of simplicity, assume you've calculated the sample standard deviation and gotten an observed value of 5. Ha ha ha. That's not likely to happen when sigma's exactly 5, that you'll get S is 5. But just for the sake of fun, comparison, simplicity, I'm going to use the same number there. But it does represent something different. It's the same number 5, but here that's a population standard deviation, assumed to be known as an exact number. Here, this is an observed value of the sample standard deviation. If I took a different sample, I'd get a different value, right? Just like when you do confidence intervals, if you do another sample, you're going to get a different confidence interval. When you do a hypothesis testing, you do another hypothesis test with a new random sample, you're going to get a different decision possibly about rejecting the null or not, a different p-value. Instead of being less than alpha, it might be bigger than alpha. That could happen. Random sampling produces random results, though you hope it's still consistent with the theory. My rejection region, once again, could be the same kind of rejection region, though I'd want to think about it in terms of t instead of z. I could say the critical or rejection region is the set of all t's such that t is less than or equal to negative 1.5, where I guess I'd have to think about degrees of freedom. Yeah. If n is 25, that means I got to use 24 degrees of freedom, n minus 1. With the t distribution, you got to think about degrees of freedom. So my alpha in this context, maybe you're doing this on a completely new piece of paper, but I'm using the same piece of paper. My alpha in this context, doing something analogous to this, I'd probably want to write it like this. I've been using my calculator today for sake of ease. You should check these things with the table as well, both the normal table in the first case, standard normal table, and the t distribution in the second case. With the t distribution, you got to look at the degrees of freedom. That's along the left side. And the critical values are only for certain values of alpha, like 0.05 or 0.01. Calculator is going to give you more precise values that won't necessarily be such round numbers. We do have TCDF as an option here. Negative 1.5, 24 degrees of freedom. What's going to happen here before I do this? Remember, the t distribution looks like a bell-shaped curve as well, centered at 0. It looks like a standard normal, except it's got a bigger variance, a bigger standard deviation. It's more spread out. So because of that, we should expect more area to the left of negative 1.5, less area in the center, more area at the tails than we did with the normal. With the normal, we got about 7%, 6.7%. We should get something slightly bigger here. Maybe not big enough to still not round to 7%, but let's see. It still does round to 7%, but if you round to 2 decimal places, it's 0.073, whereas this one was about 0.067. So if we use this as my critical region, I'm going to reject if my observed value of my test statistic is less than or equal to negative 1.5, then my probability of a type 1 error is about 7.3%, as opposed to 6.7% when I knew the population variance. You might say these are slight enough differences to not make much of a difference in practice. But it does when you got lots of tests that are going on. You know, Gossett from that brewing company, it made a difference for his company as far as their profit margins. And they outcompeted their competitors. I think. I'm assuming that actually. What's the test statistic? It's similar to this, except instead of Z, it's T. I guess I should use a red pen. Well, I used I switched my colors. I'll use a red pen again here. It's still capital X bar minus mu naught in the numerator, but in the denominator, it's instead of sigma over square root of n, it's S over square root of n, where this is really a capital S. T distribution with n minus 1 degrees of freedom. I'm not going to put a tilde and an n comma 0, 1 because it's not that. By putting a subscript of n minus 1, I'm saying it's got a t distribution with n minus 1 degrees of freedom. Once again, let's assume X bar takes on an observed value of 18.37. The test stat is going to be called T instead of Z, but since I picked S to be the exact same number as sigma, I will get this exact same value here. Okay, realize again that in practice, if you knew sigma was 5, probably S is not going to be 5, though you'd hope it'd be close to 5. It's just because I picked S to be the same, because I felt like it, that we get the same number here. The p-value then, so this t-stat is in the rejection region. We are going to reject the null. I could think of it in terms of a p-value as well. P-value, I can't write the word value. Probability that capital T sub 24 is less than or equal to 18.37. Sorry. Probability that capital X bar is less than or equal to 18.37 given mu is 20. But now that gets computed using a t distribution with 24 degrees of freedom. We got a p-value of 0.00056 here. Remember, t distribution is a little bit more spread out, a little bit more area in the tails. We'll get a slightly bigger number here. TCDF again. Change this to a negative 3.26. Still 24 degrees of freedom. Get a slightly bigger number, 0.00166. Okay, yeah, I mean, it's a slightly bigger number compared to 0, but it is about twice as big, technically speaking, as this number here. And if it was a closer call to reject the null, we're definitely rejecting the null here, but if it was a closer call, it's possible we would reject the null in this case, but not in this case. Which should you use? Which approach? It depends on how the problem is phrased. If you know sigma squared or sigma, you use this approach. If you do not know it, you would use this approach, and you need S, and you need to compute S from your calculator. As far as whether the rejection region approach should be used or the p-value approach, you should be able to do both. Usually you don't do both in the same problem, but you should be able to do both either in any situation. Sometimes the book tells you, sometimes they don't. You might have to decide on your own. It's probably simpler to use the p-value approach. That's a bit simpler.